Welcome to Science for Sleep. I am glad you are here. Tonight we're going to travel to a part of the solar system that most people have never thought about. A cold, dark, strange region between the giant planets. A place where the rules we thought we knew about asteroids and comets simply do not apply. Today, we are going to talk about Chiron. Chiron is one of the most unusual objects in our solar system. It is not a planet, it is not a comet, it is not an asteroid. The scientists have been arguing about exactly what it is ever since it was discovered in 1977, and in 2023, just 2 years ago, it revealed a secret that nobody expected. A secret that changed how we think about small objects in the outer solar system entirely. It has rings, 2 of them, around a body the size of a small country. We will get to that. But first, let us understand what Chiron is, where it came from, and why the story of one small icy object in the darkness between Saturn and Uranus tells us something profound about the solar system we live in. Comfortable. Dim the lights if you have not already, and let us begin. The Palomar Observatory sits on a mountain in Southern California, about 90 kilometers east of San Diego, at an altitude of just over 1,700 meters. It is a place built for patience, for long quiet nights, for staring at the sky and waiting for the universe to show you something new. On the night of October 18th, 1977, the astronomer at work was a man named Charles Cowell. He was reviewing photographic plates, large glass plates coated in light-sensitive emulsion, the standard tool of sky survey work in the pre-digital era. His job was simple in description and exhausting in practice. Compare images of the same region of sky taken on different nights and find anything that had moved. Stars do not move, not in the span of days or weeks. But solar system objects do. Planets, asteroids, comets, they all drift against the background of fixed stars following their orbits around the Sun. Find a moving object and you have found something in our own solar system. Cowell found something, a faint object, moving slowly, much more slowly than a typical asteroid in the inner solar system. The slowness itself was informative. The slower an object moves across the sky, to the farther away it generally is, this object was barely creeping. Whatever it was far. He measured its position from multiple images and calculated a preliminary orbit. And then he stopped. The orbit placed the object between Saturn and Uranus, at approximately 18 times Earth's distance from the Sun, in a region of the solar system that, according to every model and every expectation of the time, should have been essentially empty. And not the asteroid belt between Mars and Jupiter, and not the Kuiper belt beyond Neptune, which had not even been discovered yet. Between Saturn and Uranus, in the middle of nowhere. Cowell checked the calculation again. It was correct. He had found something that should not have been there. Something that had no name, no category, and no explanation. He called it 1977 UB. Later, he would give it a proper name. He called it Chiron. In Greek mythology, Chiron was a centaur, and a creature with the upper body of a human and the lower body of a horse, half one thing, half another, belonging fully to neither world. But unlike the other centaurs, who were wild and violent, Chiron was wise, gentle, learned. He was the greatest teacher in the ancient world, the tutor of Achilles, Jason, and Asclepius, the god of medicine. Cowell chose the name because the object, like the centaur, sat between 2 worlds, between asteroid and comet, between the known and the unknown, yet between the categories that science had carefully built and the messier reality of what the solar system actually contained. What Cowell could not have known, 1977, what would take decades of subsequent observation to reveal, was just how perfectly the name fit. Because Chiron the centaur, in the mythology, was also the son of Kronos, the son of Saturn, and Chiron the solar system object orbits near Saturn, the father, the son, separated by the mythology and separated by space, and connected by both. Sometimes the universe names things before we do. For 11 years after its discovery, Chiron was classified as a simple asteroid. Unusual in its location, yes. Puzzling in its orbit, certainly, but inert. A cold, dark, rocky body drifting between the giant planets, catalogued as minor planet number 2060, filed and largely set aside, then in 1988, astronomer Brian Marsden was reviewing a series of observations of Chiron and noticed something that did not fit. Chiron was brighter than it should be. Not dramatically brighter, not obviously brighter to the naked eye. Chiron was never visible to the naked eye, period. But when you measure the precise magnitude of an object over time, and compare it to what the mathematics of reflected sunlight predicts, and a small unexplained excess of brightness stands out like a wrong note in a familiar melody. Chiron was playing a wrong note. In 1989, astronomers Karen Meech and Michael Belton made the observation that resolved the mystery. Looking carefully at Chiron through a telescope, they saw that the object was not a sharp star-like point of light, the expected appearance of a distant asteroid. It was slightly fuzzy, slightly spread out, surrounded by a faint halo of diffuse material, a coma. And a coma is the cloud of gas and dust that surrounds a comet's nucleus as solar heating causes the surface ices to sublimate, to transform from solid directly into gas, carrying dust particles with them into space. The coma is what makes comets look fuzzy rather than sharp. It is the unmistakable signature of cometary activity. Chiron, filed as an asteroid, orbiting between Saturn and Uranus at -200 degrees Celsius, had a coma. This was not supposed to happen. And here is why Chiron's coma was so surprising, and why it forced a fundamental revision of how astronomers thought about cometary activity. Standard comets. The comets we know from history books and school lessons, the ones that grow spectacular tails and light up the night sky, are driven by one primary mechanism: water ice sublimation. When a comet approaches the inner solar system and its surface temperature rises above approximately 150 degrees Kelvin, as the water ice on and just below its surface starts turning to gas, the gas expands outward, carrying dust, forming the coma and eventually the tail. But this mechanism requires warmth. It requires the comet to be relatively close to the Sun, within roughly 3 to 4 astronomical units at most. Beyond that distance, the solar energy reaching the surface is simply too low to drive water ice sublimation in any meaningful way. Chiron's perihelion, its closest approach to the Sun, is at 8.5 astronomical units, and more than twice the distance at which water ice sublimation becomes negligible. At that distance, water ice sits frozen and inert. The surface temperature is around 70 Kelvin, -200 degrees Celsius. Water ice does not sublimate at 70 Kelvin. Full stop. And yet Chiron had a coma. Something was sublimating. Something was driving activity. Some substance was turning from solid to gas and creating the halo that Meech and Belton had observed. The answer, but when scientists worked it out, was a category of ice that most people never think about. Not water ice. Something far more volatile. Something that turns to gas at temperatures far colder than water ice ever could. Carbon monoxide, carbon dioxide, nitrogen, methane. These are the super volatile ices, substances whose sublimation temperatures are so low that they will turn to gas even in the extreme cold of the outer solar system. Carbon monoxide, the most volatile of the group, begins sublimating at around 25 Kelvin, just 25 degrees above absolute zero. Carbon dioxide sublimes at roughly 80 Kelvin, nitrogen at 63, methane at 91. At Chiron's surface temperature of 70 Kelvin, water ice is entirely frozen, but carbon dioxide and nitrogen are actively sublimating. Carbon monoxide certainly is. The Sun's heat, and even at 8.5 astronomical units, even reduced to less than 1% of its intensity at Earth's surface, is sufficient to drive these super volatile ices from solid to gas. This is what Chiron's coma is made of. Not the water and dust clouds of inner solar system comets, but a ghostly haze of carbon monoxide and other super volatiles sublimating in the deep cold of the outer solar system. This discovery had two enormous implications. First, it told us something profound about Chiron's composition. The inner object containing significant carbon monoxide ice must have spent a very long time in an extremely cold environment, because carbon monoxide evaporates so readily that any object that had experienced significant solar heating would have lost all its CO ice long ago. Chiron still had CO ice. That meant Chiron had been cold, very cold, for an extremely long time, consistent with a Kuiper belt origin preserved at the temperature of the outer solar system for billions of years. Second, it told us that cometary activity in the outer solar system, far from the Sun, invisible by the standards of inner solar system comet hunting, might be far more common than anyone had supposed. If Chiron was active at 8.5 astronomical units, other outer solar system objects might be too. The outer solar system, previously imagined as cold and inert, was potentially alive with subtle, faint, super volatile-driven activity. The classification problem was now acute. Chiron was undeniably active, and it had a coma. It was, by any reasonable definition, a comet, but it was also still an asteroid, a solid body, a stable orbit, a specific catalogued minor planet. It was both, simultaneously, irreducibly. The International Astronomical Union gave it two designations, Asteroid 2060 Chiron and Comet 95P/Chiron. To this day, it is one of the very few objects in the solar system to hold both an asteroid number and a comet designation at the same time. But two labels on one object did not solve the conceptual problem. What was actually needed was a new category. The scientific community solved the classification problem the way it always solves classification problems, by recognizing that the existing categories were not sufficient and creating a new one. In 1992, 15 years after Chiron's discovery, a second object with similar properties was found. 1992 AD, later named Pholus, her orbited in a similar region of the solar system and shared Chiron's ambiguous nature. More followed. Nessus in 1993, Asbolus in 1995, Chariklo in 1997. Over the following decades, the list grew to hundreds. They were all given names from Greek centaur mythology, and the class they represented was named accordingly, the Centaurs. Objects orbiting primarily between Jupiter and Neptune, crossing or coming near the orbits of the giant planets, originating in the Kuiper Belt, with physical and compositional properties that blur the line between asteroid and comet. Objects between worlds in every sense of the phrase. Chiron, discovered 15 years before the second centaur was found, was their founding member. Their prototype, the object whose existence had made the new category necessary. Today, more than 300 centaurs have been catalogued. The true population, including all objects too faint to detect with current instruments, is estimated in the tens of thousands. And Chiron remains the most famous, the most studied, and the most surprising of all of them. To understand Chiron, to understand why it is where it is and what is going to happen to it, you first need to understand the gravitational architecture of the outer solar system. Beyond Mars, 4 giant planets dominate everything. Jupiter at 5.2 astronomical units, Saturn at 9.5 astronomical units, Uranus at 19.2 astronomical units, Neptune at 30 astronomical units. These are not merely large bodies, they are gravitational powerhouses. Jupiter alone is more than twice as massive as all the other planets in the solar system combined. Their combined gravitational influence reaches outward through the entire outer solar system and beyond, shaping orbits, scattering objects, redirecting the paths of anything that comes too close. So between these 4 giants, in this region from roughly 5 astronomical units to 30 astronomical units, there is almost no orbital stability for small objects. Any small icy body that ends up in this region will, over timescales of a few million years, have its orbit dramatically altered. A close encounter with Jupiter might fling it inward toward the Sun. A series of encounters with Saturn might pump its orbit outward until it escapes the solar system entirely. There is no quiet, stable resting place in the Centaur zone. At every object there is, in a gravitational sense, passing through. This is why centaurs are defined not by where they came from or what they are made of, but by where they are right now, in unstable orbits, crossing or approaching the orbits of the giant planets, subjects of the endless gravitational pinball game that the outer solar system plays with everything small enough to be thrown around. Chiron is currently in one of those unstable orbits, and its perihelion, closest approach to the Sun, is at 8.5 astronomical units just inside Saturn's orbit. Its aphelion, farthest point, is at 18.9 astronomical units just inside Uranus's orbit. Every single orbit it crosses paths with both of these giant planets. Every orbit is another set of gravitational dice rolls, another set of small nudges accumulating into large trajectory changes. The mathematics of this situation has a name: chaos. Not disorder in the everyday sense, but mathematical chaos, a system so sensitive to initial conditions that small differences compound exponentially over time. Chiron's Lyapunov time, the mathematical measure of how quickly prediction becomes impossible, is estimated at just a few thousand years. We cannot reliably predict exactly where Chiron will be in 10,000 years. The system is too sensitive, the chaos is too real. Let us look at the specific numbers of Chiron's orbit because they tell a story. An orbital period, approximately 50.7 years. Since Chiron was discovered in 1977, it has not yet completed a single full orbit around the Sun. It reached its closest approach to the Sun, perihelion, in February 1996, 19 years after discovery. It is now moving outward and will reach its farthest point from the Sun in the mid-2020s, before beginning its long fall back inward toward its next perihelion in the mid-2040s. Perihelion distance, 8.5 astronomical units, just inside Saturn's orbit at 9.5 astronomical units. Aphelion distance, 18.9 astronomical units, just inside Uranus's orbit at 19.2 astronomical units. Orbital inclination, 6.9 degrees to the ecliptic, the plane in which most planets orbit. Eccentricity, 0.38, moderately elliptical, not circular. Current estimated diameter, approximately 218 kilometers. These numbers paint a picture of a body living on the edge. Its orbit dips inside Saturn's path and reaches almost to Uranus's path. It is perpetually in the gravitational neighborhoods of both planets. It is, in a very real sense, in the wrong place, a place where it cannot stay indefinitely. The origin of centaurs is well established by the computer simulation and theoretical modelling. They come from the Kuiper belt. The Kuiper belt is the vast ring of icy bodies beyond Neptune, extending from roughly 30 to 50 astronomical units, home to Pluto, Eris, and hundreds of thousands of smaller objects. It is a cold, remote, ancient place. And objects there have been largely undisturbed since the solar system formed 4.5 billion years ago. But the Kuiper belt is not perfectly stable. Neptune's gravity reaches into it, slowly perturbing orbits over millions of years. Occasionally, a Kuiper belt object gets nudged into a path that brings it close enough to Neptune for a more dramatic encounter. Neptune's gravity changes the object's orbit significantly, pulling its perihelion inward past 30 astronomical units, past 20 astronomical units, and into the realm of the giant planets. The former Kuiper belt object is now a centaur. From that moment, its fate is in the hands of the gravitational pinball machine. The giant planets will toss it around for a few million years, a brief time by solar system standards, and then one of several things will happen. Most centaurs, roughly 50 to 60%, are eventually ejected from the solar system entirely, and a series of gravitational encounters pumps their orbits larger and larger until they reach escape velocity and depart into interstellar space, becoming rogue objects drifting forever between the stars. A smaller fraction, perhaps 20 to 30%, migrate inward instead. Jupiter's gravity captures them into shorter period orbits, turning them into Jupiter family comets. These are the active, dusty, familiar comets of the inner solar system. Halley, Temple, Tuttle, Churyumov-Gerasimenko. All of them, in all likelihood, were once Kuiper belt objects that passed through the Centaur zone on their way inward, and a very small fraction end up in more stable configurations, longer-lived Centaur orbits that persist for tens of millions of years before the gravitational dice finally roll against them. Chiron is currently somewhere in the middle of this process, but computer simulations of its future show a wide range of possible outcomes. Ejection is most probable, but inward migration is possible. Its fate is genuinely uncertain. When Charles Cowell discovered Chiron in 1977, the Kuiper belt did not exist. Not officially, not observationally. It was a theoretical prediction, proposed by astronomer Gerard Kuiper in 1951, and by Kenneth Edgeworth even earlier, but never confirmed. The space beyond Neptune was believed by most working astronomers, though to be essentially empty. Chiron's existence was a quiet argument against that belief. If Chiron was a centaur, an object in transit between an outer reservoir and the inner solar system, then there had to be an outer reservoir. You cannot have a transit population without a source. The properties of centaurs, their composition and their orbital dynamics, pointed clearly toward a large population of icy objects beyond Neptune feeding them inward. This argument was made. It was heard. And 15 years later, in 1992, David Jewett and Jane Liu at the University of Hawaii found 1992 QB1, the first confirmed Kuiper belt object beyond Pluto. The Kuiper belt was real. Chiron had been the first evidence, the first messenger, discovered 15 years before the population it came from was even confirmed to exist. In retrospect, this makes Chiron one of the most scientifically consequential discoveries in the history of outer solar system astronomy, not because of what it was, but because of what it implied. It pointed toward a hidden reservoir of ancient icy bodies that we had not yet found, in a region of the solar system we had not yet properly explored. That reservoir turned out to contain hundreds of thousands of objects. Pluto, it turned out, was just the most famous of them. Computer simulations run backward in time, tracing Chiron's orbit into the past rather than the future, give us a rough picture of where Chiron came from. The simulations are not precise. The same chaos that makes Chiron's future uncertain also makes its deep past uncertain. Small errors in the current orbit run backward, grow into large uncertainties over hundreds of thousands of years. But the broad picture is consistent. Chiron was almost certainly a Kuiper belt object for the vast majority of the solar system's history. It orbited beyond Neptune, probably at 30 to 50 astronomical units for billions of years, cold, inert, undisturbed. So slowly accumulating cosmic radiation processing on its surface, building up the dark organic crust that makes outer solar system objects so dark and red. At some point, within the last few tens of millions of years, a blink in cosmic time, Chiron experienced a gravitational encounter that changed everything, most likely with Neptune, a close approach that tugged Chiron's orbit inward, reducing its perihelion distance from beyond 30 astronomical units to something much smaller, and eventually leading to the orbit we observe today. That moment, whenever it occurred, was the moment Chiron's clock started ticking. From that point, it was a centaur. From that point, it was doomed to a relatively brief existence in the giant planet zone before the next gravitational encounter sent it somewhere else entirely. From the perspective of the solar system's 4.5 billion year history, Chiron has been a centaur for an eye blink. It arrived recently. It will leave soon. And now we happen to be alive and looking at the sky at exactly the moment it is passing through. Here is why Chiron's Kuiper belt origin matters so much for science. The outer solar system is the solar system's deep freezer. Objects beyond 30 astronomical units have spent their entire existence in temperatures so cold, 30 to 50 Kelvin, that most chemical reactions are effectively frozen. The ices on their surfaces and in their interiors have not been melted. The organic material has not been processed by liquid water. The compositions reflect, as closely as anything in the solar system can reflect, the original composition of the outer solar system material from which they formed 4.5 billion years ago. Chiron, with its billions of years in the Kuiper belt, is among the most pristine objects we have access to. Its super volatile ices, the carbon monoxide still frozen in its interior, and sublimating slowly to drive the coma, are molecular time travelers. Carbon atoms forged in stars that lived and died before our sun was born, incorporated into the molecular cloud that became our solar system, frozen into Chiron's ice at the dawn of solar system history, and now slowly sublimating into space, where we can detect and analyze them. Every molecule Chiron releases into space is a sample of the early solar system. That every spectroscopic measurement of Chiron's coma is a reading from a 4.5 billion year old chemical record. This is what makes Chiron, and centaurs in general, so scientifically valuable. Not just their orbital dynamics or their surface properties. Their chemistry, their ancient, frozen, perfectly preserved chemistry. The message they carry from the beginning of everything we live in. For most of the history of planetary science, the ring systems were understood to be the exclusive property of giant planets. Saturn's rings were known since Galileo first observed them in 1610, though he did not understand what he was seeing, describing them as Saturn appearing to have ears. The true nature of the rings was understood by Christian Huygens in 1655. By the late 20th century, rings had been discovered around Jupiter, Uranus and Neptune as well. 4 planets, 4 ring systems. And a clear theoretical reason why: rings require large central bodies to maintain them. Smaller bodies lack the gravitational influence to prevent ring particles from sticking together and forming moons, or to confine the rings against the natural tendency of ring material to spread and dissipate. The accepted wisdom was that ring systems around small bodies, objects smaller than perhaps a few thousand kilometers, were simply not possible, or at least not stable enough to be observed. And then came 2014. Chiron, a centaur roughly 250 kilometers in diameter, discovered in 1997, was observed as it passed in front of a background star. This technique, called stellar occultation, is one of the most precise tools available for studying small solar system objects. As the object moves across the star's light is cut off briefly, and the duration and shape of that cutoff reveal the size and shape of the object with great precision. But the team observing Chariklo's occultation saw something unexpected. Before the main star occultation, before Chariklo itself crossed the star's position, there were two brief symmetric dips in the star's brightness. Small, sharp, identical on each side. And then, after the main occultation ended, the same two dips appeared again as mirror images. Rings, two of them, at about 391 and 405 kilometers from Chariklo's center. The planetary science community was stunned. The rings around a 250-kilometer object? The theory said it should not be possible, and yet there they were, narrow, distinct, real. If Chariklo could have rings, the question immediately arose, what about Chiron? The question about Chiron's rings had actually been circulating for some time before Chariklo's discovery. Earlier occultation observations of Chiron, going back to 1993 and 1994, had shown puzzling features, unexpected dips and asymmetries in the light curves that the observers had attributed at the time to jets of material from Chiron's active nucleus, rather than rings. After Chariklo's rings were confirmed in 2014, researchers went back to those old Chiron occultation datasets and looked at them with fresh eyes. Were those anomalous features actually ring signatures? The old data was noisy and limited, but suggestive. The definitive answer came in 2023, and a team of researchers, including scientists from MIT, analysed a series of stellar occultation events involving Chiron that had been carefully observed from multiple locations on Earth, using both professional observatories and a network of amateur astronomers with precise photometric equipment. By combining the data from multiple occultation events and applying sophisticated modelling, they were able to identify consistent features that could not be explained by jets or by the cometary coma. Two rings, both narrow, both real. The inner ring sits at approximately 324 kilometers from Chiron's center. The outer ring at approximately 423 kilometers. Each is only a few kilometers wide. Thin bands of dark, icy particles orbiting Chiron in the same plane as its equator. Optically thin, meaning they are not dense enough to significantly block light passing through them, but unmistakably present in the occultation data. Chiron joined Chariklo in an extremely exclusive club. There are two centaurs, both ringed, both raising profound questions about how ring systems form and survive around small bodies in the outer solar system. Let us be precise about why Chiron's rings are so remarkable, because the full strangeness of the situation deserves proper appreciation. Chiron is 218 kilometers in diameter. Its rings orbit it at distances of 324 and 423 kilometers from its center. Now this means the rings are located at distances of only about 1.5 to 2 times the radius of the body itself, just above the surface in a gravitational sense. For comparison, Saturn's most visible rings extend from about 7,000 kilometers above the cloud tops to about 80,000 kilometers out. Saturn's diameter is about 116,000 kilometers. The rings extend from less than a fraction of a Saturn radius to well over half a Saturn radius away. Chiron's rings, in terms of distance relative to body size, are actually proportionally closer to the body than many of Saturn's rings are to Saturn. This is important because it suggests that the physical mechanism keeping the rings confined, preventing them from spreading and dissipating, may have more to do with the specific distance from the body and the tidal forces at that distance than with the absolute size of the body itself. In other words, it is not that small bodies cannot have rings, and it is that rings can only survive in specific zones around any body, and we had been wrong about where those zones start and end. Chiron, a 218-kilometer icy body between Saturn and Uranus, has rings, and we now need to ask, how many other small bodies in the outer solar system also have rings that we simply have not yet had the opportunity to detect? The confirmation of Chiron's ring system immediately raised the most interesting question: how did they get there? Our planetary scientists have proposed 3 main mechanisms, each with its own logic and its own evidence. The first theory is impact origin. At some point during Chiron's existence in the Centaur zone, possibly relatively recently, within the last few tens of millions of years, a smaller object struck Chiron. The impact was energetic enough to blast material off Chiron's surface. Most of this ejected material either fell back to the surface or escaped into space entirely. But a fraction, material moving at just the right speed just below Chiron's escape velocity, went into orbit instead. Over time, this orbital debris spread out and settled into the two narrow rings we observe today. This scenario is plausible. Impact rates in the outer solar system are low, but not zero. Chiron, crossing the orbits of Saturn and Uranus, has had billions of years to accumulate impact events. A ring-forming impact is not implausible. Yet the second theory connects the rings to Chiron's cometary activity. When Chiron outgasses, when its supervolatile ices sublimate and gas rushes off the surface, most of that gas escapes into space at velocities well above Chiron's escape velocity. But outgassing is not perfectly uniform. In some directions and at some velocities, a small fraction of the ejected material may have just the right speed to achieve orbit rather than escape. Yet if this happens consistently over many perihelion passage, a ring could slowly build up from accumulated orbital debris. This theory is attractive because it links two of Chiron's most distinctive features, the coma and the rings, in a single physical story. Both would be expressions of the same underlying super-volatile ice sublimation. The third theory involves tidal disruption of a former satellite. And if Chiron captured a small moon at some point, perhaps during a close encounter with one of the giant planets, and that moon subsequently migrated inward to within the Roche limit, the distance at which tidal forces become strong enough to tear an object apart, the moon would have been shredded into debris. That debris would spread out into a ring-like configuration at approximately the distance where disruption occurred. But this scenario naturally explains the specific distances of Chiron's rings. They would correspond to the Roche limit for Chiron's mass and density, and it would mean the rings are relatively recent, formed after the capture and subsequent disruption of a former satellite. One of the most puzzling aspects of Chiron's situation is that the rings and the coma coexist. This should not be easy to achieve. Cometary outgassing is violent. When gas rushes off the surface of an active comet, and it carries dust with it. Some of that dust achieves escape velocity and becomes part of the coma. Some of it falls back to the surface, and some of it, in principle, could bombard the ring material, disrupting its structure over time. Additionally, the gas itself, flowing outward from the nucleus through the ring plane, exerts pressure on the ring particles, a force that over time should push them into different orbits, broadening and dispersing the rings, yet the rings are there. They have survived despite the active cometary environment. Several explanations have been proposed. The cometary activity may be sporadic, active near perihelion, when Chiron is closest to the Sun, but largely dormant near aphelion. If the rings are geologically recent, formed by impact or tidal disruption within the last few million years, they may simply not have had time yet to be significantly disrupted by the outgassing. Alternatively, there may be a replenishment mechanism, material continually being added to the rings from Chiron's surface activity at roughly the same rate it is being removed by outgassing. A dynamic steady state rather than a static structure. The coexistence of rings and coma around Chiron makes it, as far as we know, unique in the solar system. No other object simultaneously maintains both. And understanding how this is possible is one of the most interesting open questions in Chiron science. And it will require either a spacecraft visit or many more years of careful Earth-based observation to resolve. Chiron's orbit is beautiful in the way that precarious things can be beautiful. It is perfectly poised, a path that carries it to the realm of Saturn and back to the realm of Uranus, crossing both planets' orbits in its 50-year circuit. From the outside, it looks orderly, measured, but predictable. It is not. The technical measure of orbital stability is the Lyapunov time, the timescale over which small uncertainties in an object's position grow into large uncertainties in its predicted future trajectory. For Earth, the Lyapunov time is measured in tens of millions of years. For Jupiter, it is even longer. The inner solar system, while not perfectly stable on astronomical timescales, is stable enough for any practical purpose. For Chiron, the Lyapunov time is estimated at just a few thousand years. A few thousand years! This means that we cannot reliably predict with precision where Chiron will be in the year 12,000. Not because our measurements of its current orbit are imprecise, they're actually quite good, but because the system itself is intrinsically chaotic. Tiny differences in initial conditions, differences smaller than we can ever measure, compound exponentially over time. Yet 2 simulations of Chiron's future started from positions differing by a centimetre will diverge completely within a few thousand years. This is not a failure of mathematics. It is the mathematics telling us something true about the system. Chiron's orbit is genuinely, mathematically unstable. Its future is genuinely uncertain. Despite the chaos, statistical approaches can tell us something meaningful about Chiron's future. Rather than trying to predict exactly what will happen, planetary scientists run thousands of simulations of Chiron's orbit, each starting from slightly different initial conditions within the measurement uncertainty, and record what happens to each version of Chiron over millions of years. The results give a probabilistic picture. Not a certain prediction, but a map of possibilities with associated likelihoods. The most likely outcome, occurring in roughly 50 to 60% of simulations, is ejection from the solar system. The gravitational encounters with Saturn and Uranus gradually pump Chiron's orbital energy higher and higher. Eventually, after a particularly close encounter with one of the giants, Chiron's velocity exceeds the solar escape velocity at that distance. Its orbit becomes hyperbolic, an open curve rather than a closed ellipse. And Chiron departs the solar system permanently. It becomes an interstellar object, drifting through the galaxy for the rest of time. The second most likely outcome, perhaps 20 to 30% of simulations, sees Chiron migrate inward instead. Encounters with Saturn redirect it toward Jupiter. Jupiter, the gravitational giant, captures it into a short-period orbit. Chiron becomes a Jupiter family comet, an active inner solar system comet. If this happens, and if Chiron retains enough volatile material, it would become an extraordinarily spectacular comet at 218 kilometers, and it would be by far the largest known cometary nucleus. Its coma and tail in the inner solar system, where water ice sublimation would kick in to add to the super-volatile activity, would be unlike anything seen in recorded human history. Both of these futures are millions of years away. In the meantime, Chiron continues its 50-year circuits, patient, steady, carrying its ancient cargo of frozen chemistry through the cold outer solar system. Though one of the most interesting aspects of Chiron's behaviour is how its cometary activity varies with its orbital position. Near perihelion days, when Chiron is at its closest to the Sun, solar heating is at its maximum. The super-volatile ices on and near the surface sublimate most vigorously. The coma is at its most developed. The brightness excess above the bare nucleus prediction is greatest. Chiron is, in a sense, most awake near perihelion. In 1996, when Chiron last reached perihelion, observers tracked its brightness carefully and confirmed the expected increase in activity. The coma was well developed. Occasional outbursts, sudden short-lived increases in brightness caused by the exposure of fresh volatile material were observed. As Chiron moved away from perihelion after 1996, its activity gradually diminished. The coma faded, the brightness excess decreased. By the late 2000s, Chiron was behaving more like a quiet, inert minor planet than an active comet, though subtle brightness variations continued to hint at ongoing low-level activity even at greater distances. Chiron will reach its next perihelion in the mid-2040s. As it slowly approaches over the coming years, we expect to see its activity gradually increase. The coma will brighten, outbursts will become more frequent, and for the first time, we will be able to observe a Chiron perihelion passage with the James Webb Space Telescope and with the Vera C. Rubin Observatory, instruments that did not exist during the 1996 perihelion, and that will reveal details of Chiron's activity that were previously completely inaccessible. The next Chiron perihelion will be one of the most scientifically valuable events in outer solar system astronomy in the coming decades. To fully appreciate why Charles Cowell chose the name Chiron, yet you need to know the myth, not just the basic facts, but the texture and the detail of the story, because the correspondence between myth and object is striking in ways that go well beyond the obvious. In Greek mythology, the centaurs were a race born from the union of Ixion, a mortal king and a cloud goddess. They were wild, violent, given to drunken excess. At the wedding of the Lapith king Piritaus, the centaurs were invited as guests and proceeded to attempt to abduct the Lapith women, starting one of the most famous battles in Greek myth, the Centauromachy. But Chiron was not one of those centaurs. He came from a different lineage entirely. His father was Kronos, the great Titan, lord of time, who in Roman mythology became Saturn. His mother was the sea nymph Philyra, because Kronos had transformed himself into a horse to avoid his wife Rhea discovering the encounter. Chiron was born as a centaur, but one of divine and titanic ancestry rather than the common centauric stock. The difference in parentage translated into a profound difference in character. Where other centaurs were savage, Chiron was wise. where they were ruled by animal instinct. He was guided by knowledge and reason. He mastered medicine, archery, music, and philosophy. And he became the greatest teacher in the ancient world. His cave on Mount Pelion was a school where gods sent their most important sons to learn what no ordinary teacher could teach them. Achilles, the greatest warrior in the Trojan War, trained by Chiron from childhood in archery, the arts of war, and the music of the lyre. Jason, the leader of the Argonauts, taught by Chiron everything he would need for the quest for the Golden Fleece. Asclepius, the son of Apollo who became the god of medicine, learned the healing arts from Chiron, whose knowledge of medicinal plants and treatments was unsurpassed by any being on Olympus. Even young Heracles, the greatest hero of Greek myth, received wisdom from Chiron, though the encounter would later end in tragedy. The tragedy of Chiron begins with a misunderstanding. Heracles, pursuing a group of hostile centaurs, fired his arrows, tipped with the poison of the Lernaean Hydra, and a substance of such lethal potency that even a scratch was fatal. In the chaos of the battle, one arrow struck Chiron. Not intentionally. Chiron was not Heracles' enemy. It was an accident, a stray arrow in a confused fight. But the result was devastating. The Hydra poison began working immediately, causing unbearable, unending pain. And here is the cruelty at the heart of the myth. Chiron was immortal. As the son of a Titan, he could not die. The poison that would have granted any mortal the mercy of death simply condemned Chiron to eternal agony. He could not heal. The Hydra's poison was beyond even his own extraordinary medical knowledge. He could not die. He could only suffer endlessly in a wound that refused to close. Eventually, Chiron made a choice. He negotiated with Zeus, offering to take the place of Prometheus, the Titan who was being punished for giving fire to humanity, yet chained to a rock and having his liver eaten daily by an eagle. If Prometheus could be freed, Chiron would give up his immortality in exchange. Zeus agreed. Prometheus was freed. Chiron relinquished his divine gift and died, and was placed among the stars as the constellation Centaurus, immortalized in a different way. A being who could not fit into one category, who taught and shaped the greatest heroes of the age, who was wounded by an accident, not by malice, not by fate, but by the chaos of a messy universe, who eventually surrendered the thing that was supposed to protect him, because the wound was worse than death. Look at Chiron, the solar system object, through the lens of this myth, and the correspondence is remarkable. Chiron the object cannot fit into one category. It is asteroid and comet simultaneously, a creature of two natures, belonging fully to neither. It orbits near Saturn, near the realm of Kronos, its mythological father. It is, in a sense, wounded, losing material to space, slowly being diminished by the sublimation of its ices. The coma, the outgassing, the slow loss of its ancient frozen interior to the solar wind. These are the wounds Chiron bears as it falls inward from the outer cold toward the sun's heat. Its orbit is temporary. Like Chiron's immortality, its current existence in the Centaur zone cannot last. It will be ejected or transformed. The thing that defined it, its in-between existence, at its location between Saturn and Uranus, will end. And it was, in a very real sense, the teacher of solar system science. The discovery of Chiron taught us that the space between the giant planets was not empty, that cometary activity could occur far from the Sun, that the Kuiper belt existed, that rings could form around small bodies. Every major advance in outer solar system science in the past 50 years has been informed directly or indirectly by what Chiron showed us. Chiron the Centaur was the greatest teacher in Greek mythology. Chiron the solar system object may be the greatest teacher in the history of outer solar system astronomy. There is a before Chiron and an after Chiron in solar system science. The dividing line is 1977, and the difference between the two sides is substantial. Before Chiron, the solar system was understood, in broad terms, as a relatively simple categorical system, rocky planets in the inner solar system. The giant planets in the outer solar system, asteroids in the belt between Mars and Jupiter, comets coming from the distant Oort cloud on long, elliptical orbits, clean categories, clear locations, a solar system that behaved for the most part the way the textbooks said it should. The space between the giant planets was not thought of as a habitat for small bodies. It was a transit zone at most, a region through which comets might pass on their way from the outer solar system to the inner, but not a place where objects lived and orbited and had complex physical properties. Chiron ended that picture. A single object discovered by one astronomer on one mountain in California was enough to show that the picture was wrong. The giant planet region was not empty. It contained objects with properties that defied the existing categories, and objects that forced a fundamental rethinking of the solar system's architecture and the diversity of the bodies it contains. The rethinking that followed Chiron's discovery has not stopped, it has only accelerated. The most consequential thing Chiron implied, the most important downstream effect of its discovery, was the existence of the Kuiper Belt. As discussed earlier, Chiron's existence as a centaur implies a source population. Centaurs come from somewhere. That somewhere had to be a large reservoir of icy objects beyond Neptune. The properties of centaurs, their compositions and their dynamics, pointed specifically toward a trans-Neptunian population. When David Jewett and Jane Liu confirmed the Kuiper Belt in 1992, the discovery was not coming out of nowhere. It was the confirmation of what Chiron had been implying for 15 years, and the Kuiper Belt turned out to be extraordinary. Not just a thin ring of distant icy objects, but a rich, diverse, populous region home to Pluto and Eris and Makemake and Haumea, home to hundreds of thousands of smaller objects, home to the source population for virtually all the comets we see in the inner solar system. A major structural component of the outer solar system, previously unknown and unsuspected by most astronomers. All of this, the entire Kuiper Belt, with all its implications for how we understand the solar system, was foreshadowed by Chiron, but by one object found by Charles Cowell on photographic plates at Palomar Observatory in 1977. It is not an exaggeration to say that the modern understanding of the outer solar system traces its origins, in large part, to that single discovery. Chiron also forced a fundamental reconsideration of how we classify solar system objects, and more broadly, of whether any classification system can fully capture the diversity of nature. The asteroid-comet binary, and the idea that small solar system bodies are either rocky and inert or icy and active, and that these are distinct categories, was a foundational assumption of planetary science before 1988. Chiron broke it. By being unambiguously both, a solid body with a stable orbit and an active body with a cometary coma, it showed that the binary was false. Nature had produced something that sat in neither box. The response, creating the centaur category, was the correct scientific response, but it opened a larger question. If the asteroid-comet distinction was more porous than we thought, what other categorical distinctions were we using that nature did not respect? The answer turned out to be many. Pluto, discovered in 1930 as the 9th planet, turned out to be a Kuiper Belt object, not a planet in any meaningful dynamical sense. Its eventual reclassification in 2006 was, at least in part, a consequence of the conceptual framework that Chiron's discovery had helped create. Active asteroid, main belt asteroids that display cometary activity, have been discovered in the inner solar system, further blurring the asteroid-comet distinction. Interstellar objects, Oumuamua and Borisov, showed that the solar system could be visited by material from other star systems, adding a new category that did not previously exist. The taxonomy of the solar system is now vastly richer and more honest than it was before 1977. It acknowledges the existence of centaurs, scattered disk objects, trans-Neptunian objects, active asteroids, contact binaries, interstellar visitors. The categories are more numerous, more specific, more accurately reflecting the actual diversity of what the solar system contains. Chiron made the first and perhaps most important tear in the old categorical fabric. The richer understanding we have today grew through that tear. Chiron was the first centaur, but it is not alone. Today, the centaur catalogue contains more than 300 confirmed objects, with the true population estimated in the tens of thousands once you account for objects too small or too faint to detect with current instruments. The centaur population is, in a sense, a sample of the Kuiper Belt, a cross-section of the outer solar system reservoir. They're pulled inward by the Neptune and currently passing through the giant planet region. Studying centaurs is, in some ways, studying the Kuiper Belt at closer range than the Kuiper Belt itself allows, since centaurs are generally closer to Earth than the objects they originated from. The diversity within the centaur population is striking. They range in size from Chiron and Chariklo at roughly 200 to 250 kilometers down to objects just at a few kilometers across. They range in colour from extremely red, dark reddish surfaces attributed to heavy organic processing, the darkest objects in the solar system, to neutral grey with surfaces that appear to be dominated by different material. This colour bimodality is one of the most puzzling features of the Centaur population. The two colour groups are statistically distinct. There is a gap in the colour distribution rather than a smooth continuum. Several hypotheses have been proposed. The two groups may originate in different regions of the Kuiper belt, or the colour difference may reflect different evolutionary histories, including differences in the degree of cometary resurfacing that has occurred. Chiron itself is relatively grey, less red than the reddest centaurs. This is consistent with the idea that its cometary activity has been resurfacing it, exposing fresh, yet less processed ice from below the dark organic crust that would otherwise dominate its surface appearance. Among Chiron's centaur siblings, the most important for understanding Chiron's rings is Chariklo. Chariklo, discovered in 1997 and estimated at about 250 kilometers in diameter, was the first small body found to have a ring system in 2014. Its rings are two narrow bands at 391 and 405 kilometers from its center, designated C1R and C2R. C1R is about 7 kilometers wide and significantly more opaque than C2R, which is only about 3 kilometers wide. The comparison between Chiron's ring system and Chariklo's is instructive. Both objects are large centaurs, the two largest well-studied members of the class. Both have two narrow rings. The ring dimensions are similar. The orbital dynamics of the rings around both objects face similar challenges of confinement and maintenance. That the fact that both of the largest known centaurs have ring systems is almost certainly not a coincidence. It suggests that ring formation is more likely around larger centaurs, perhaps because larger objects have higher surface gravity, making it easier for ejector to achieve orbital rather than escape velocity, or because larger objects are more likely to have captured satellites that can subsequently be disrupted into rings. If ring formation is correlated with size among centaurs, and if there are tens of thousands of centaurs in total, then the number of ringed centaurs could be in the hundreds or even thousands, all of them too small and too distant to detect their ring systems from Earth with current technology. The outer solar system may be full of small ringed worlds that we simply cannot yet see. Beyond Chiron and Chariklo, the centaur population includes several other large and scientifically interesting objects. Pholus, the second centaur discovered, then in 1992, is notable for its extraordinary redness. Its surface colour is among the most extreme of any solar system object, reflecting a surface dominated by complex organic material processed over billions of years of cosmic radiation. Pholus has an orbit that extends from just inside Saturn's orbit out to beyond Neptune, a wider range than Chiron's, and one that makes it particularly subject to gravitational perturbations from multiple giant planets. Xenopolus, discovered in 1995, is another red centaur, somewhat smaller than Chiron, currently between Saturn and Uranus. Its name comes from the centaur Asblis in Greek mythology, who had the power of prophecy, an appropriate name for an outer solar system object that, in a sense, carries information from the past. Bienor Boas, discovered in 2000, is roughly 200 kilometers in diameter and has been studied for evidence of variability. And its relatively large size and its position in the Centaur zone make it another candidate for ring detection in future occultation campaigns. The centaurs taken as a whole are a population in transition, objects borrowed temporarily from the outer solar system, passing through the giant planet region on their way to whatever their final fate will be. They carry the chemistry of the early solar system in their frozen interiors. Sure, they carry the history of the outer solar system in their surface colours, and some of them, at least two and possibly many more, carry rings that we are only just beginning to understand. The James Webb Space Telescope, launched in December 2021 and fully operational since mid-2022, represents the most powerful astronomical instrument ever built for studying cold, distant objects in the infrared. And its 6.5 meter segmented primary mirror collects roughly 7 times more light than the Hubble Space Telescope. Its instruments are optimized for infrared wavelengths, the part of the spectrum where cold objects emit most of their thermal radiation and where the molecular fingerprints of ices, organics, and gases are most distinctly imprinted. For outer solar system science, Webb is transformative. Objects that were previously detectable only as single points of light, with barely enough signal to measure a rough color, can now be analyzed spectroscopically. their surface compositions read in detail from the specific wavelengths of light they absorb and emit. Chiron has been among the outer solar system targets for Webb observations. The results have provided the most detailed picture yet of its surface composition. The Webb's near-infrared spectroscopy has detected clear signatures of carbon dioxide ice on Chiron's surface, a super volatile ice consistent with its active outgassing behaviour. There are also tentative detections of carbon monoxide and methane features. The spectra show absorption features at wavelengths characteristic of complex organic material. Tholins, the dark reddish polymers produced by radiation processing of simple organic ices over long timescales. The thermal infrared data from Webb's MIRI instrument, the mid-infrared instrument, has provided improved constraints on Chiron's size, albedo, and surface thermal properties. The measurements are consistent with a surface that is heterogeneous, different areas with different thermal properties, possibly reflecting the patchy distribution of fresh ice exposed by outgassing activity versus the older, darker organic crust that covers most of the surface. And our best current estimates of Chiron's basic physical properties come from a combination of thermal observations, stellar occultations, and reflected light measurements refined over decades. Diameter, approximately 218 kilometers. The uncertainty on this measurement is probably plus or minus 15 to 20 kilometers, not because our observations are poor, but because Chiron's coma complicates the measurements, adding some reflected light from the coma itself that is difficult to fully separate from the nucleus signal. Shape, approximately spherical. At 218 kilometers, Chiron is near the threshold at which self-gravity becomes strong enough to pull a rocky, icy body into a roughly spherical shape. It is probably not a perfect sphere, minor asymmetries are expected, but it is not the highly irregular, lumpy shape of smaller asteroids and comet nuclei. Albedo, approximately 0.11 to 0.17. This means Chiron reflects between 11 and 17% of the sunlight that falls on it. Relatively dark by the standards of inner solar system objects, but moderately bright for the outer solar system. The albedo is higher than the darkest Centaurs and Kuiper Belt objects, consistent with the idea that cometary activity is continually exposing fresh, slightly brighter surface material. Rotation period, approximately 5.9 hours. So Chiron rotates once on its axis every 5.9 hours, a moderate rotation rate, faster than most large Kuiper Belt objects, but within the normal range for Centaurs and minor planets generally. Rotation axis orientation, not well determined. This is scientifically important. The orientation of the rotation axis affects the seasonal pattern of solar heating across the surface, which in turn affects where and when outgassing activity is most intense. A better determination of the rotation axis orientation is a priority for future Chiron observations. The study of Chiron's coma has advanced considerably since the initial discovery of cometary activity in 1988 to 1989. Modern observations with large telescopes and sensitive spectrographs have allowed astronomers to measure not just the presence but the composition and structure of the coma with increasing detail. Then carbon monoxide has been directly detected in Chiron's coma, confirming that CO sublimation is indeed one of the drivers of the activity. The production rate of CO, the amount being released per second, varies with Chiron's distance from the Sun in a way that is broadly consistent with sublimation theory, though with significant variability that suggests the activity is not purely driven by smooth, heliocentric, distance-dependent heating. And the coma shows evidence of jet-like structures, regions of the surface where outgassing is significantly more intense than the average. These active regions are likely areas where fresh, volatile, rich material has been recently exposed, perhaps by small impacts, perhaps by the thermal cycling of the surface as Chiron rotates, or perhaps by the physical collapse of surface structures as the underlying ices sublimate and remove support. Occasional outbursts, brief and dramatic increases in coma brightness and production rate continue to be observed. These outbursts are not predictable in advance and can occur at any orbital position, not just near perihelion. They are likely caused by the sudden exposure of large amounts of fresh volatile material, the solar system equivalent of a geyser, or the uncapping of a long pressurized reservoir of gas beneath the surface. And among the most scientifically significant aspects of Chiron's composition is the presence of complex organic material, carbon-containing compounds of various kinds in various stages of processing, on its surface and in its coma. Organic chemistry is everywhere in the outer solar system. The dark reddish surfaces of Centaurs, Kuiper Belt objects, as many irregular moons of the giant planets are dominated by tholins, the complex organic polymers produced over millions and billions of years when simple molecules like methane, nitrogen, and carbon monoxide are exposed to ultraviolet radiation and cosmic ray bombardment. Tholins are not a single compound, but a family of compounds with a wide range of molecular weights and structures. Chiron's surface, as revealed by spectroscopy, shows clear evidence of tholin-like organic material. The dark, relatively low albedo surface, particularly in the areas that appear to be the oldest and least resurfaced, is consistent with a thick coating of processed organic material built up over billions of years. But beneath that processed surface layer is something much more interesting. Fresh, unprocessed organic material that has been protected from radiation by the overlying layers. And this is the material that is released when outgassing excavates fresh surface, when the sublimation of underlying ices creates channels and voids that expose the interior to space for the first time. The gas phase chemistry of Chiron's coma, the molecules detected in the gas cloud surrounding the nucleus, includes not just simple super volatile ices, but also more complex organic species. Understanding the full organic inventory of Chiron's coma is one of the primary scientific goals of future observations. The relevance of Chiron's organic chemistry to the question of life's origin on Earth requires some context. Life on Earth requires at minimum three things: liquid water, a source of chemical energy, and organic molecules, the building blocks from which biological molecules can be assembled. Of these three requirements, the third, the supply of organic molecules, has historically been the most mysterious. How did the first complex organic molecules on early Earth get there? The traditional assumption was that they were produced on Earth itself, by lightning discharges in the early atmosphere, as famously demonstrated by the Miller-Urey experiment in 1953, or by chemical reactions in hydrothermal vents, or by ultraviolet-driven chemistry in the early atmosphere and oceans. That these processes are real and important. But increasingly the evidence suggests that delivery from space, from comets and asteroids that bombarded the early Earth, was also a significant source of organic material. The Murchison meteorite, which fell in Australia in 1969, was found to contain more than 90 different amino acids, including many not found in Earth life. Other carbonaceous meteorites have been found to contain nucleobases, the building blocks of DNA and RNA. The cometary material appears to be rich in organic chemistry. Chiron, as a representative of the Kuiper Belt reservoir, as an object actively releasing its frozen organic inventory into space, is part of this broader story. Objects like Chiron, falling inward toward the inner solar system, as they eventually do, either as centaurs or as comets, deliver their cargo of frozen organic material to the inner solar system. Some of this material reaches Earth. And understanding Chiron's organic chemistry is, in a small but real way, understanding part of the story of how life on Earth came to be. In 2017 and 2019, the solar system received two confirmed visitors from other star systems, 1I/Oumuamua and 2I/Borisov. Borisov, the second and more scientifically accessible of the two, was a comet. It had a coma and a tail, and was amenable to spectroscopic analysis. When astronomers analysed its spectrum, they found something remarkable. Borisov's composition was surprisingly similar to solar system comets: the same water ice, the same carbon monoxide, the same dust properties, an object that had formed around a completely different star, in a completely different part of the galaxy, had chemistry that closely resembled objects in our own solar system. This similarity has a profound implication. Cometary chemistry is apparently universal or close to it. The physical and chemical processes that produce icy objects rich in super volatile ices and organic material are general properties of planet formation, not peculiarities of our own solar system. Wherever planetary systems form, they produce objects like Chiron. The outer reaches of planetary systems across the galaxy are full of Chirons, frozen, ancient, organically rich time capsules. And if organic chemistry is universal in the outer regions of planetary systems, and if that material is delivered to inner planets by cometary and centaur-like objects falling inward, then the organic precursors of life may be delivered to habitable planets across the galaxy. The universe may be seeding its habitable worlds with the chemical ingredients for life, systematically, inevitably, as a consequence of the physics of planet formation. Chiron in this picture is not just a strange object between Saturn and Uranus. but it is one of the universe's chemical couriers, carrying its ancient cargo toward an uncertain destination, just as countless similar objects have done in star systems across the galaxy for billions of years. This fact bears repeating because it is easy to forget in an era of extraordinary space exploration success. We have sent spacecraft to Mercury, Venus, Earth's moon, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, and several Kuiper belt objects. Till we have landed on the moon, Mars, Venus, Titan, and several asteroids. We have orbited and studied comets at close range. The New Horizons spacecraft flew past Pluto in 2015 and revealed an astonishing world that nobody had predicted. A world with active geology, a complex atmosphere, and surface features that defied every expectation. But the Centaurs, the class of objects that Chiron founded, at the transitional bodies between the Kuiper belt and the inner solar system, remain completely unvisited. Not one spacecraft has ever made a close flyby. Not one camera has ever captured a Centaur surface at resolution better than a few pixels across. Everything we know about Chiron, its size, its rings, its coma, its composition, has been inferred from observations made at distances of hundreds of millions or billions of kilometers. This is not because Centaur missions are impossible, yet it is because they are expensive and time-consuming, and the competition for resources in planetary science is fierce. There are many compelling destinations and limited funding. The Centaurs have been passed over repeatedly in favour of destinations that were judged more immediately compelling. But the scientific case for a Centaur mission is strong and getting stronger. The lesson of New Horizons is clear and relevant before the Pluto flyby in July 2015. That Pluto was a blurry dot. Even in the best Hubble Space Telescope images, it showed up as a few pixels with hints of colour variation but no discernible surface features. Its atmosphere was known to exist but barely characterised. Its moons, 5 of them, were known to exist but poorly understood. Pluto was essentially a mystery with a name. New Horizons spent 9 years travelling to Pluto, and on July 14, 2015, it made its closest approach, skimming within 12,500 kilometres of the surface at 14 kilometres per second. The few hours of closest approach, it returned images and data that filled in the blank that Pluto had been for 85 years. The images showed Tombor Regio, the heart-shaped basin of nitrogen ice that became the iconic image of the flyby, mountains of water ice 3 kilometres tall, and a complex multi-layered atmosphere with hazes visible hundreds of kilometres above the surface. Evidence of glacial flow, sublimation transport, and ongoing geological activity driven entirely by internal heat and atmospheric cycles with no significant solar energy input. The scientific papers generated from New Horizons data number in the hundreds. The understanding of Pluto, and of the Kuiper belt in general, was transformed. Objects that had been thought of as simple, inert, or frozen worlds were revealed to be geologically complex, active, and diverse. A Chiron flyby would almost certainly be similarly transformative. Chiron is, in many respects, more interesting than Pluto was before New Horizons. It has rings, which Pluto does not. It has active cometary behaviour, which Pluto barely has. And it represents a class of objects, centaurs, about which we know almost nothing at close range. Several concepts for Centaur missions have been studied by planetary scientists, though none has been formally approved for development. The primary challenge is distance. Chiron, at 8 to 19 astronomical units, is far from Earth. Even with gravitational assist manoeuvres, using the gravity of planets to bend and accelerate a spacecraft's trajectory, a mission to Chiron would require a travel time of at least 8 to 12 years from launch to arrival. The spacecraft would need to operate reliably for decades. Its power source, solar panels generate negligible power at Chiron's distance, would almost certainly need to be a radioisotope thermoelectric generator, or RTG, converting the heat of radioactive decay into electricity. A flyby mission, the simplest architecture, would send a spacecraft up past Chiron at high speed, gathering images and data during the few hours of closest approach. This is the New Horizons model. So the scientific return per dollar is high. Even a brief flyby would transform our understanding of Chiron's surface, geology, and ring system. The limitation is that a flyby cannot study time-variable phenomena, like the cometary activity in detail. It would capture a single snapshot rather than a time series. An orbiter mission, more expensive, more complex, but scientifically much richer, would slow down and enter orbit around Chiron, spending months or years studying it in detail. An orbiter could monitor outburst events as they happen, track the evolution of the coma through a perihelion approach, characterize the ring particle sizes and compositions by flying through them, and map the entire surface at high resolution over multiple orbits. A sample return mission, the most ambitious possibility, would collect material from Chiron's surface or coma and return it to Earth for laboratory analysis. Direct analysis of Chiron material in a laboratory, but where the full arsenal of analytical chemistry can be brought to bear, would provide immeasurably more compositional information than any remote sensing measurement. The prebiotic organic chemistry of Chiron's surface could be characterized in detail, potentially illuminating both the chemistry of the early solar system and the question of life's ingredients. Imagine a spacecraft approaching Chiron. The journey has taken 10 years. The ship has crossed the orbit of Jupiter. Just the orbit of Saturn. The sun behind it has shrunk to a bright star, till the brightest object in the sky, but a point of light rather than a disk. The temperature outside the spacecraft's hull is around -200 degrees Celsius. Ahead, growing slowly from a point to a disk, is Chiron. At first, from a few million kilometers away, Chiron appears dark, very dark, darker than coal. The surface reflects only about 15% of the faint sunlight reaching it. But as the spacecraft approaches, details emerge. The roughly spherical shape, not a perfect sphere, but close. Slight asymmetries in the outline. The rotation is visible. The entire body is turning, completing one rotation every 5.9 hours. Features appear, rotate into view, and disappear over the visible limb. The coma is visible, a faint diffuse haze surrounding the nucleus, extending outward in the direction away from the sun. In the spacecraft's cameras, a sensitive instrument specifically designed for this environment, the coma appears as a subtle brightening around the nucleus. Jets, narrow streams of gas and dust erupting from specific points on the surface, are visible as bright streaks within the coma, pointing away from the surface in directions determined by local topography and the rotation of the body and the rings. The rings are visible from this distance as a faint, thin disk around the equator, not as spectacular as Saturn's rings in photographs, but present and real. Two narrow bands of dark, icy particles moving in their quiet orbits just above the surface. As the spacecraft reaches closest approach, flying within a few thousand kilometers of the surface, the details resolve. The surface is dark and heavily textured. Craters, the inevitable record of impacts over billions of years, are visible across the surface, and some are old and degraded, their rims softened by subsequent sublimation and resurfacing. Others are fresher, with sharper edges and brighter interior walls where excavation has exposed less processed material from below the dark surface crust. The active regions, the areas where outgassing jets are erupting, appear different from the surrounding terrain. These areas are slightly brighter, suggesting fresher surface material. And some show evidence of surface modification, areas where the sublimation of underlying ices has created depressions, collapsed surfaces, or layered cliff faces where the stratigraphic history of the surface can be read in the exposed rock and ice. The ring plane seen from within looks different than it does from a distance. The individual ring particles, ranging from microscopic dust grains to pebble-sized fragments, are not individually resolvable. But the overall structure of the rings is clear. The inner ring, slightly denser than the outer, casts a faint shadow on the surface below at certain sun angles. The gap between the two rings is measurably empty. The whole scene is lit by the faint, cold light of a distant sun, a light that is less than 1% as intense as sunlight at Earth. In this light, shadows are long and dramatic. The peaks of crater rims catch the light while the floors remain in deep shadow. The jets catch the light as they emerge from the dark surface, glowing briefly, before dispersing into the coma. It is a world that has never been seen by human eyes, strange and cold and beautiful, in the way that ancient things often are. The science return from even a brief Chiron flyby would be transformative, but the most valuable measurements would come from instruments that directly sample Chiron's environment rather than simply imaging it from a distance. And a mass spectrometer in the coma would measure the precise molecular composition of the gas Chiron is releasing, identifying every significant molecular species present and measuring their relative abundances. This would be the direct chemical reading of the early solar system's outer reservoir, the most detailed compositional analysis ever obtained for a Kuiper belt-derived object. And a dust analyzer, an instrument that physically captures and analyzes individual particles passing through it, could characterize the solid material in the coma and potentially in the ring system. The size distribution, composition, and structure of the dust particles carry information about the physical processes that produce them: sublimation, outgassing, impact gardening of the surface. Combined with close-range imaging, temperature mapping, and measurements of the local magnetic field environment, a Chiron flyby would answer questions that have been open since 1977, and inevitably raise new questions that nobody has yet thought to ask. That is how science works. Every answer opens a door. There is a philosophical lesson encoded in Chiron's existence, and it is worth sitting with for a moment. Human beings are categorizing animals. We are cognitively compelled to organize the world into named groups, to find the thing that two objects have in common and give that commonality a label, then use that label to make predictions. This is one of our most powerful cognitive tools. It allows us to reason about unfamiliar objects by reference to the familiar categories. It allows us to communicate efficiently about complex phenomena. It allows us to build scientific theories that generalize across instances. But categories are human constructs. They are maps of the territory, not the territory itself. The universe does not organize itself according to the labels we find convenient. Nature does not know the difference between an asteroid and a comet. It does not know that rings are supposed to be around giant planets only. It does not know that the space between the giant planets should be empty. Chiron is the solar system's way of reminding us of this. When Chiron was discovered, that it was forced into the asteroid category, not because it was obviously an asteroid, but because that was the closest available box. When the coma was discovered, a second box was hastily added, the comet designation. When neither box was adequate, a new box was created, Centaur, and that new box has proven to be one of the most scientifically productive concepts in modern planetary science. The Centaur category opened the way to the discovery of the Kuiper belt, to the understanding of the comet delivery mechanism, to the recognition of ring systems around small bodies. A new category, created to accommodate one anomalous object, turned out to describe a population of tens of thousands of objects and illuminate fundamental aspects of solar system dynamics. This is how science progresses at its best, not by defending existing categories against anomalous data, but by allowing anomalous data to reveal the inadequacy of existing categories and then building better ones. Chiron was not the first rule breaker in astronomy, and it has not been the last. The history of science is largely a history of objects that did not fit the existing categories and forced the creation of new ones. Uranus, discovered in 1781, was the first planet found by telescope. Before that, the planets were defined as the wandering lights visible to the naked eye. Yet Uranus broke that definition and forced the realization that the solar system extended beyond the visible. Ceres, discovered in 1801 in the gap between Mars and Jupiter where Bode's law predicted a planet, seemed at first to be the missing planet. But over the following decades, more and more objects were found in the same region. Ceres was not a planet, but the largest member of a new category, the asteroid belt. Pluto, discovered in 1930 and classified as the 9th planet, was reclassified in 2006 as a dwarf planet when the Kuiper belt it was part of became undeniable. The category of dwarf planet, created to accommodate Pluto and Eris and the other large Kuiper belt objects, is now one of the standard categories of planetary science. Oumuamua, detected in 2017 as the first confirmed interstellar visitor to the solar system, forced the creation of an entirely new category, interstellar objects. And objects that are formed around other stars and travel through the galaxy as free-floating bodies, occasionally passing through stellar systems. A category that had been theorized but never confirmed until Oumuamua appeared. Each of these rule breakers in its time was a challenge. Each required the scientific community to revise its picture of what existed and how it worked. Each eventually produced a richer, more accurate understanding of the universe. Chiron was one of the most productive rule breakers of the 20th century, and it continues to break rules, most recently in 2023, when its ring showed that even a body this small could maintain a ring system that should, by the old rules, not have been possible. There will be a next Chiron, not literally. There will not be another object named Chiron, but there will be another discovery that does not fit, and another object whose properties confound the existing categories and force the creation of new ones. Another moment when the universe shows us that our picture of it is incomplete. The Virasi-Rubin Observatory, currently beginning full science operations in Chile, will survey the entire visible southern sky hundreds of times over its 10-year mission. It will find hundreds of thousands of new solar system objects, and among them will almost certainly be objects with properties that nobody has predicted. Objects in unexpected locations, objects with unexpected activity, objects that combine characteristics in ways that our current categories do not accommodate. We do not know what those objects will be. By definition, if we knew, they would not be surprising. They would just be predicted objects eventually found. Interesting, but not what a rule we're using. The next Chiron will be something we could not have predicted. Something that makes us say, this should not exist, and yet here it is. What do we do with it? And the answer, as always, will be, look carefully, think deeply, revise the categories, build a better map. The universe is always ahead of us. The best we can do is follow with curiosity and humility. Chiron has been part of our solar system for 4 billion years. For almost all of that time, it was quiet. And orbiting in the Kuiper belt beyond Neptune in temperatures 40 to 50 Kelvin above absolute zero. The sun from that distance was just the brightest star in the sky, a point of light, not a disk, not a warmth. Chiron orbited that bright star once every 250 years, slowly and without drama. Nothing happened, nothing visible, nothing dramatic. The slow work of cosmic ray bombardment processed the surface molecules into complex organic material. Yet the interior stayed frozen. Temperatures so cold that even carbon monoxide, the most volatile of the super-volatile ices, remained locked in the ice. For billions of years, nobody knew it existed. Nobody could have known. It was too far, too cold, too dark to detect with any technology that existed before the mid-20th century. And then, within the last few tens of millions of years, something changed. A gravitational encounter, probably with Neptune, altered Chiron's orbit. The perihelion began moving inward, closer to the Sun, closer to Saturn, into the Centaur zone, into the realm of the giant planets. And Chiron woke up. The super-volatile ices began sublimating. The coma appeared. The brightness varied. In 1977, Charles Cowell photographed a faint moving dot on a glass plate in California, and, without knowing it, became the first human being to see Chiron, to cast photons reflected from its surface onto a light-sensitive surface, creating a record of its existence. 4 billion years of anonymity ended in that moment. Right now, as you listen to this, Chiron is out there, between Saturn and Uranus, moving at a few kilometers per second along its 50-year elliptical orbit, currently moving outward from the Sun on the long, slow arc toward aphelion near Uranus's orbit, before it turns and begins the equally slow fall back towards Saturn. The coma surrounds it, a tenuous halo of carbon monoxide and carbon dioxide and dust, extending outward from the nucleus for perhaps tens of thousands of kilometers. Faint, ghostly, invisible to any unaided eye, detectable only by the most sensitive instruments. The rings orbit it, 2 narrow bands of dark, icy particles moving in silent circles at 324 and 423 kilometers from the center, each particle following its own individual orbit, each orbit slightly different from the others. Of the rings as a whole maintaining their narrow structure through mechanisms we do not yet fully understand. The nucleus, 218 kilometers of ancient rock and ice and frozen super-volatile chemistry, rotating once every 5.9 hours, active regions on the surface releasing gas, inactive regions building up their dark organic crust. The two sides of Chiron's nature, the asteroid and the comet, coexisting in the same body simultaneously, and as they have for the millions of years since it entered the Centaur zone. No spacecraft observes it, no camera has ever captured its surface. It is known only through light, reflected and emitted light, analysed at great distances, revealing the silhouette of a world we have never truly seen. Chiron will not always be there. Within a few million years, an eye blink in the life of the solar system, it will leave its current orbit, ejected into interstellar space by the gravitational influence of Saturn or Uranus or Jupiter, or captured inward to become a comet, or perhaps, in some small fraction of possibilities, migrated into a longer-lived Centaur orbit for tens of millions of years before finally departing. Whatever the outcome, the Chiron that exists right now, between Saturn and Uranus, ringed and active and ancient, will eventually be gone from this configuration. The solar system is not static. And objects come and go through the Centaur zone. They borrow their place there for a few million years and then move on. This temporariness is part of what makes Chiron meaningful, rather than diminishing it. A permanent object is unremarkable. It is always there, always the same, always available. A temporary visitor passing through is worth paying attention to. It will not always be accessible. The window to observe and understand it is finite. We are, right now, in the window. And we have been in the window, since 1977. We have decades, possibly millions of years before the window closes. The question is what we do with the time we have. Chiron, the object, will eventually leave, but the knowledge it has produced, the understanding it has enabled, will remain. It taught us the Centaur class exists. 300 confirmed members, tens of thousands estimated, an entire population of outer solar system objects passing through the giant planet zone that we did not know about before 1977. It hinted at the Kuiper Belt 15 years before the Kuiper Belt was confirmed. The entire modern understanding of the outer solar system, the Kuiper Belt, the scattered disk, the Oort cloud connection, the comet delivery mechanism, traces its observational origins in part to Chiron. It showed that cometary activity occurs far from the Sun, driven by supervolatile ices. This expanded the definition of where in the solar system chemical activity is possible, and opened new questions about how outer solar system objects evolve. It demonstrated, with Caraclow's help, that ring systems form around small bodies. This rewrote the theory of ring formation, and raises the possibility that rings are far more common in the outer solar system than we ever imagined. And it embodied a lesson that goes beyond any specific scientific finding. The universe is stranger and more diverse than our categories suggest. The things that break our categories are not problems to be managed. They are gifts, opportunities to understand more, to see more clearly, to build a better picture of the world we inhabit. Chiron will leave, the knowledge stays. Tonight, we have travelled a long way. We began with a man at a telescope in California in 1977, and finding a faint moving dot on a glass plate and not quite knowing what to make of it. We followed Chiron through its classification problem, the slow realization that it was both asteroid and comet, that it needed a new category, that the Centaur class it founded was not a curiosity, but a gateway to understanding the entire outer solar system. We learned that Chiron carries super volatile ices from the Kuiper Belt, ancient pristine chemistry from the formation of the solar system, are slowly being released as it falls toward the inner solar system. We discovered its rings, two narrow bands of dark icy material orbiting just above its surface, confirmed in 2023, raising fundamental questions about how ring systems form and survive around small bodies. We explored its mythology, the ancient Greek centaur who was wise and wounded and temporary, who sat between worlds and taught the greatest heroes, and who in mythology was the son of Saturn as this object in space orbits near Saturn. We looked at it through the most powerful telescope ever built, the James Webb Space Telescope, and saw its surface composition and its cometary activity in unprecedented detail. We imagined visiting it, a spacecraft approaching after 10 years of travel, cameras resolving the dark ringed jet-studded surface for the first time, and we sat with what it means, an object that breaks categories, that teaches by its very existence that is temporary and ancient and strange and beautiful, that is Chiron. Right now above you, above the clouds, above the atmosphere, out in the cold and the dark between Saturn and Uranus, Chiron is moving, slowly, steadily, in its 50-year circuit around the Sun. It does not know it has been named. It does not know that in 1977, a man in California photographed it and changed how we understand the solar system. And it does not know that in 2023 scientists confirmed its rings, or that the James Webb Space Telescope has been studying its surface, or that you are here tonight, thinking about it as you drift towards sleep. It is just there, moving, ancient, strange, neither asteroid nor comet, neither planet nor moon, neither permanent nor gone, between worlds. Like so much that is most interesting in the universe, existing in the space between the categories, in the blur at the edge of understanding. It's in the place where the old maps run out and the new ones have not yet been drawn. Sleep well, the solar system is stranger and more wonderful than the textbooks say, and somewhere between Saturn and Uranus, a ringed cometary world is quietly proving it. Good night.